Let's start today's class. First, as you asked me to say few words about the quantum chaos, so let's start by that. But it is uh, it is very hard for me to say anything about quantum chaos, okay? Because so if you know that what does the quantum system means, so basically quantum system means if I say in a very lucid layman way, then one would say that quantum mechanics is the study of the realm of very microscopic particles. So in that microscopic level, not all the deterministic model that we have studying from the Newtonian era or that we are studying here in this course are not applicable. So people has experimentally found that in that realm of that microscopic world, the things are not quite certain, quite deterministic. They are actually probabilistic in nature. So the if anyone asks the question, right, suppose a problem like suppose there is a hydrogen atom. So we know that hydrogen atom means there is a nucleus of one proton, and there is a one electron which is orbiting around this nucleus. Now if anyone asks what is the position of this electron at any moment, so the answer will be there is no certain position of this electron. So electron to get the electron in a certain position, you only can calculate what is the probability that the electron you will find if you do an experiment in a laboratory, what is the probability that you will find that electron from a r distance from the nucleus. That probability you can find, but you can never know, you will never know exactly where the electron is. So that is that quantum mechanics is the real quantum mechanics is actually probabilistic by nature. And how that we know that in the all the other governing laws such as means all the other governing laws follows the Newtonian equation, whereas the quantum follows the Schrödinger equation. That is, if means the quantum where means another thing in the quantum mechanics is that we cannot express the state of a electron or proton by its position and momentum or velocity or energy. In this way we cannot express its state in the real world, such as if you want to say something about that earth and sun, you have to means we can express the state, that means position state of the earth and the sun in terms of in the terms of position, momentum, these like things. But in the quantum realm we cannot express the state by these quantities, that position, that's velocity. So how we express that? We express by a state vector, the psi, which is basically a imaginary number. So in reality there is no significance to this psi, but from this actually psi contains all the information of this r, this p, this v, this e. So there are certain operator. If you operate psi with that thing, you will get energy. Suppose you will get energy eigenvector. Suppose you have an operator e, so like a function. So you have a function e, so we have know that what does the function means and what does map means. So e is a function which operate on psi, and it will give you back some energy state and psi again. So this is called the eigenvector. So this is that thing. So and this psi, as we know how the population evolved, so we know that the population in the population biology, the state vector is state is denoted by the number of individuals in the population, that is n, and its time evolution dn dt we are after, that is r into n into 1 minus n by k. Similar to this in quantum mechanics, the state vector evolve under time in this way, that del psi del t is I h cut Hamiltonian into psi. So in this way this state vector this psi evolve. Now the problem is, so wherever you will see the chaos, so what is the problem with chaos? So whatever you will see the chaos, the basic ingredients is needed, that is non-linearity in the time evolution equation. That means, but here you see that there is not any non-linearity. Here you see that in the logistic equations, as for example, so xn plus 1 is r into xn 1 minus xn. So you see that xn plus 1 depends on the xn square. So that is non-linear relationship. But here you see that this is not non-linear by nature. So this is linear by nature. The psi is linear to linearly dependent on this function. The time evolution Schrödinger equation that actually tells the fate of the quantum mechanics or the quantum particle. So that is linear in nature. So that is one problem to deal with quantum chaos. So this is linear in nature. But what happens? So since we know that some classical, this is called Hamiltonian, if you know something about that. So it is basically the energy operator. So energy, so it's basically a function. What you can think that basically it's a function. If you suppose that is function in this logistic map, the function is we know that map, a definition of map, if I applied on some x0, it takes to x1 some other value. Here suppose this is the map. If you operate on psi, you will get back some energy and psi again. So you will get back the energy and psi again. This is called the energy operator. That's why it's called energy operator, since if I operate or if I operate on psi, it will give back the energy. Now, and this h can be calculated classically. Classically means that by Newtonian mechanics you can calculate this classically, this Hamiltonian. Now if anyone knows, suppose that the three body problem. So in the three body problem, Poincaré discovered that there is a chaos. So so first of all, one thing, that quantum state cannot say, quantum state can never shows chaos like classical one. But what can it shows that in some cases that classical counterpart, that means which is counterpart means a system which is same Hamiltonian age. And if I know that this Hamiltonian, the classical motion, that Newtonian motion if chaotic, so if I know that the classical motion or the Newtonian motion under this Hamiltonian is chaotic, so in the quantum chaos we are after about that. If I say that since this Hamiltonian shows chaotic behavior in the classical regime, does it shows anything in the quantum regime? So since it shows the chaos in classical regime, does it show anything, any trace of this chaos in quantum region, then you will find that yes, indeed it shows something, but it does not show chaotic state, chaotic behavior of the psi. It shows something, some irregular behavior of this energy eigenstates. This is called the eigenstate. So this is called eigenstate. So energy eigenstate. So this energy. So you will see some irregular behavior in energies. So that is actually quantum chaos. So this is the just the surface level of this quantum chaos. And if anyone want to understand really what the quantum chaos is, I would suggest that means to know some preliminary knowledge of this quantum is very helpful, will be very helpful for them. And anyway, the chaos we are actually dealing with here, so chaos part is remains same, because whenever you dealing chaos in classically, the way we are dealing in this course is the same. The thing will be there, only thing is that a little bit knowledge of quantum mechanics is needed. So that's it. Is it clear? Means little bit clear, Subhusaji? Then we will go to the next thing. Okay. Now let's see, then let's jump towards what we have learned previously. So we have seen that seen that what is the orbit diagrams looks like, and we have drawn orbit diagrams, and from that orbit diagram, okay, let me show it here. So this is the orbit diagram that we have seen in the previous class. So we have seen that in this orbit diagram, so we can see where the chaos is appearing. So and where the periodic orbit is there. So periodic orbit means only limited numbers of point is there in the final behavior of that system, and this is means this in this region of R, this is 2 periodic orbit. Here 4 periodic, here 8 periodic, and after a red line, that is R infinity, that we know that at some point of R, every single point by split into 2 other points. So here there was 2 period, and 2 period after bifurcating, splitting into 2, it become any point become 2 points. So this is 4 point orbit, and again this 4 point, every point of this 4 point split into further 2, and it makes 8 points orbit. So it goes on and up to a point where is R equal to infinity, that has a value that's nearly about, it's about, this is red line, so it's 3.57 near about that. And after that it become that the system become chaotic. What does it means? So far we have seen that that in this region there are a lot of dense points is there. That means the system there is no single or multiple attractor kind of thing. There is no fixed points, and there is no periodic orbit at all. So last, that means the orbit actually moving here and there, it does not follows any periodic orbit or any fixed point. So that's why we are saying that this the motion of this orbit is quite irregular, and we say that there may be a chaos, and we know that this is the chaos. We will see today's class by the Lyapunov experiment that there is chaos. So that's the first thing. And in this region what we have seen, another thing, so in this region you will see that there is a very much intricate play between chaos, this dense region of these points, and some window of the periodic behavior. So as for example here you will say, you actually see that there are actually periodic points. So this is 1, 2, 3, 4, 5, 6. So 6 orbit periodic orbit is there. So much. So if I increase r, so increase r means if I go in this direction, you will see there is a large window, biggest large window of the periodic orbit at somewhere between 3.82, so 3.8284, exactly 1 plus root 8. So where you see there is a 3 period orbit is appearing. Now the question is how this 3 periodic orbit is appearing. So that there was so let's see how this orbiting, and we see that by period doubling that what is called it, that saddle node bifurcation, this happens. That also we have studied in the previous class by use of the graph. So let me recall what we have done. So we have seen that how this appears. So, and we already know what does period 3 orbit means. We know that period 3 orbit means it should be a fixed point of fq. So if it is with fq x0 has a solution x0, then we can say that x0 the x0 is a 3 periodic point, and other point will be that if I apply on x0, it will give me some point x1, so 1 point this, 1 point that, and if I another x1, it will give some point x2. So these 3 point is actually these 3 point actually the periodic point, and if I again apply on fx2, it will get back x0. So that is that. Now let's see graphically what is actually happen, how the saddle node bifurcation is creating this 3 period orbit. Okay, so you see if I draw, so fq should be look like this, and okay. So this is my drawing is horrible, I know, but it should look like this. So you see this is f cube, this is f cube x, this is x, this is f cube. Now you see there are only two fixed points are there. One is this fixed point and another is this fixed point, and this fixed point is nothing but r minus 1 by r, and we know that this fixed point is corresponding to the solution fx equal to x. So that's all. Now when you increase r, what happens? When we increase r, you will see that this value will sink, this value will further down, this also further drop, this also further drop, and these hills also rise. This hill will be rise, all hill will rise. So at some point you will see exactly at values r equal to 1 plus root 8, this hill exactly touches this value will exactly touch the identical line, this value also exactly touch the identical line. The identical line will become the tangent to this every 3 point, this and this point. Now if I further increase r, then what happens? So previously there were none fixed point, but now what happens by saddle node bifurcation, you will see when it cross like this, you will see there are two fixed point will appear. One will be this one and another will be this one, and you see that the slope of one point, this is higher and this is one will be steeper and one will not that much steeper. So from that the steepness you can calculate that which fixed point is actually stable. Okay. Ah, it's maybe problem of this internet. Is it now okay? I don't know how it will be, how it will be, or is it now also breaking? Then I will rejoin this meeting. Hi Subhajji, I am audible. Ha. I think that's. Let me rejoin. Now I suppose my voice is not breaking that much. I don't know. Okay, then it is fine. So you will see that one point, the tangent of one point become more steeper than another. You will find that only one of these two fixed point will be stable. So naturally we see that this fixed point becomes stable and this is unstable. Here also you will find the similar trend. So one stable and one unstable. And here also you will see the creation. You will observe the creation of two fixed points. One will become stable and another will become unstable. So that's how you will get another 3 point, which is this. Suppose this point will be x0, this point will be x1, and suppose this point will be x2. So these 3 points. So suppose this point is x0. So if you apply f on this x0, the orbit will take you to here, and if you take f on x1, it will take to x2. So that's how there is a creation of this 3 periodic orbit by saddle node bifurcation. And so nothing new about it. So this is actually new because this is the creation of the 3 periodic orbit by saddle node bifurcation. That's all. Now if the question is that if I further increase this, or let me say this in this way, that let first, so this is the periodic 3 periodic orbit. 3 periodic orbit. Now if we see here, so there is a sharp transition between disorder and order. So this is the 3 periodic orderic things, most periodic things that we can thought, and just below this R 1 plus root R there is a chaotic behavior. So this is the smooth transition between the chaos and 3 periodic orbit. Now let's see what happens there. So this is actually called the intermittency root of the chaos, where from periodic behavior suddenly the chaos appears. It is called the intermittent root of the chaos. Intermittent root of, it's called intermittent root of chaos. So let's first see. So we know that where does this sharp or disorder to order to order transition, we know that at r equal to 1 plus root 8, and it is nearly about, since it's a irrational number, so it is actually 3.8284. now if I take any lesser value than this, it will show some it should show some chaotic behavior. So there will be, you see, so r less than this 3.8284 should be, it should go to this region, so this disorder or chaos. So let's see some behavior or so orbit at some point, like let's see some point at orbit at r equal to 3.8282, suppose. Let's see. So okay, at maybe 3.9 also you can see, at 3.9 also. Yeah, now you can see that what happened to this thing, that at 3.9 that chaotic regime, so this is not quite, this is too much chaotic, so let me 3.8282, then it will be more clear. 3.8282, what I am saying, why I am choosing this, it will be clearer. So okay, now it will be clearer. So you see one thing, Subhusaji, that it should be chaotic, the region should be chaotic because r equal to 3.8282, so r is lesser than 3.84, and from our previous orbit diagram we know that should be chaotic, but here it does not look that much chaotic. What does it look like? So it look like most of the thing is like periodic. So you see that this is the 3 periodic, this red 3 dot corresponding to 60, 61 and 62th iteration, and you see that this is like quite like periodic orbit. But what happens here, so sometimes you see there is some region which is kind of noise kind of thing, so anyone who will see this kind of signal will say that this is the system is behave perfectly like or perfectly periodically, but in between some noisy thing is there, and this, the appearance of this noise, and no one can predict where these noisy things will appear. So actually what you are saying, some ghost of the 3 periodic orbit in between in the region of the chaos. So in the 3.8282 theoretically there should not be possible of any appearance of the 3 periodic orbit, there should be always the chaotic, but what we are seeing, some ghost of this 3 periodic orbit. So this is called the intermittent root of the chaos. So when you suppose that from you are in the region of 3 point, suppose let me say that 3.83, so if I continuously decrease from here, so from here this r equal to 1 plus root 8, if I continuously decrease the values of r, you will see that previously it was the periodic, and then continuously it will not suddenly jump to all chaotic. What happens, some kind of this chaotic behavior will appear in between of this perfectly fine periodic behavior. So this is called the intermittent chaos or intermittent. This is called the intermittent chaos. The chaos is not always but somewhere in between. So why this ghost where anyone should not observe the periodic thing, why anyone see these 3 periodic orbit, why the ghost is appearing? So that we will also again explain through the use of map. Is it clear that intermittent root of the chaos সবুজ আছে? Okay, let's see then why you are seeing that 3 periodic ghost in between the chaotic region. So let's see that. So we will see in the cobweb diagram that will be 3 point. Let's see here also 3.82. Yeah, so you see here does not you see that there is a one thing you observe that this blue dot, if it touches this point, it will remain here for a larger time. It will not remain here forever, but it will actually remain here for large time. If it was in the okay, you see that this now escape from this region. So you see here it stays. Now first of all let us show. First of all let observe that thing that I am suppose. First observe the periodic motion, means when FQ has a fixed point, then what will appear, what will happen. So you see that this point will be some fixed point, so it reaches to the fixed point. So here it will stay for forever, it will not leave from here. Now when I decrease a little bit, 3.8 these, if I decrease the value of r by 0.002, what it will happen? So from here you see it will remain there, but it will eventually leave from here. So you can see there is a little bit, every time it will shift a little bit. If you can see, so you can see that the shift of little bit, but it will stay longer here. So when I am, this is 3.828, when I am staying there, you will see that the system is chaotic, it will not remain there. But whenever it reaches to any of the near about fixed points, so near about this region, so wherever this region or this region, they remain there for a long time. So that is actually reason of that the 3 periodic orbit. So let me explain it hereby. So suppose you take any region where, suppose I am taking this region, so where, so it's look like that. Now whenever randomly the orbit reaches closer to this channel, so this is the identical line, this is suppose a part of FQX. So whenever the orbit reaches between this channel, so to move from here to here, it takes a very longer time. And when it will means what is remain in between this channel, so what happens when it remain in between the channel, so you see that x does not change much, so x remain between these two things, these very narrow things, means if remain here to here, so that x will not change very much. So here you can say that if I apply FQ on some point, suppose xi, it will approximately remain to xi. That's why it does not go from here, it remain there for quite long time. And if it remain there quite long time, that means upon applying FQ xi, FQ means iteratively 3 times f upon any initial condition xi, it will not change very much, it remain approximately xq. And we know that if any xq satisfied this, then we say this is a 3 periodic orbit. three periodic orbit. So that's why you see for a longer time it remain in between this channel. That's why it follows this equation, and since this follows this equation, it actually look like kind of that it is actually showing a periodic behavior, but actually it is not showing periodic behavior, since it takes quite longer time to pass this channel. That's why it seems like the periodic behavior. That's why we are seeing the three periodic orbit or the ghost of the three period in between the chaos. So that is the it's called the intermittent root of the chaos, or means okay. So Bhusaji, is it clear why we are seeing that chaotic means why we are seeing the periodic region in the it means where actually we only should see chaos, but now we see the ghost of three period orbit. Why it is so? Is it clear now? Okay. So there are a famous example of. Okay. Are you saying something? Huh. Look. Yeah, near about fixed point, not exactly that. Fixed point has not been created till that point of art. So you see there is a quite long gap. So here in the, so you see there is a quite long gap between this identical line and this. There is the fixed point has not been created until that value part, but if I increase a little bit r, there will be a creation of the fixed point, but where that creation the fixed point will appear, near about that point that orbit remain longer. You are right. So that's all. So there are very examples of this intermittent chaos. So there is a one example is the laser pulse in the cavity, where you see that if you change the parameter, previously you see the intensity of the pulse actually periodically like this way, this periodically changing intensity. Now when you change the parameter, that means the tilt in the mirror in the laser cavity, you will see that somewhere in some places you will see some erratic motion, in some chaotic motion, and it continuously remain periodic most of the time. Now if you increase furthermore this burst of this chaos, you will see quite often. Now you cannot say where this burst appears, so that's the most interesting thing. Since the chaos, although these chaos or logistic equations are deterministic thing, but also you see that this appearance of burst you cannot predict theoretically. It is appear as randomly like noise. In between this periodic signal you will find some part or some here and there the burst of chaos, and when you increase that parameter furthermore, you will see that this burst of the chaos become very often. So and when you increase a lot more the parameter a little bit more, you will see the chaos is everywhere, no sign of this periodic orbit. Now there is another example which quite similar, but I don't know how similar it is, but in my view that is quite similar. That is means in the there is a disease called that arterial fibrillation, AF, which is a disease of heart, where the chaotic electric signals causes, means where the upper chamber of the heart, because of the upper sometimes the what happens, the upper chambers of heart beats irregularly. Because of that, you will see some random chaotic motion in between the normal electrical signal of this heart. So this is quite like that intermittent chaos. So intermittently you will find randomly somewhere here and there, because of that upper chamber of the heart beating chaotically. That's why you will see that intermittent chaos. So that is the one example, that could be one example of the intermittent chaos. And because of this irregular thing, because of this unpredictable thing, you cannot predict actually when this burst of chaos will appear in between the random rhythmic motion of the normal heart. So that's it. So that's the intermittent root of chaos. So we learned two root of chaos so far. One is that period doubling root, another is that intermittent root of the chaos, where first of all there will be a periodic motion, and if I change the parameter, and you will see somewhere some burst of chaos will appear randomly, and if I increase further, the whole system will become chaotic. That is the intermittent chaos, root of intermittent chaos. That's how the chaos appears. And the first thing is period doubling. You see that every time whenever you just increase, any periodic point will split into two, and if I increase further, split into two. So this continues and until it reaches the infinite period orbit, r infinity, and if I increase a little bit from that, and the chaos will appear in the system. So there is a two way of chaos up till now. Now the next question is, what happens if I suppose if I move from this intermittent root of chaos to previously where was we, from the 3 periodic orbit. So now the question is, one question remains here. So that is, if I increase r furthermore, so if I increase r furthermore, what happens? So you will find that every, similar to the period doubling bifurcation, you will find that every this stable periodic point will actually split into two in the period doubling bifurcation if I increase furthermore, and again it will find this root of chaos, and you will see the system will be chaotic again. And what will happen then means, if I go back to here, okay, if I go back to here, so you see that from here, every from if I increase furthermore, you can see that every periodic point will split into two. This is split into two, this is also split into two, and first period doubling bifurcation happen, and 3 period orbit becomes 6 period orbit, and again that period doubling bifurcation appears. So if you can see, then from 6 to 6 to 12, so like this. So after 3 periodic, if I increase, so what happens? So first will be 3, then 3 into 2, then 3 into 2 square, 3 into 2 4, so that like this, and you find that 3 into 2n, and when it become 2 means it become at some point at r3 infinity, it will become infinite period orbit, and then the chaos will appear. So if it is the case, then what should look like this near about this point? So let's see, near about any any point of the 3 periodic orbit should look like the whole picture. So this is our assumption, because this is our answer or assumption, because you see from here how the chaos appears by period doubling. So previously what was there was one periodic orbit means fixed point. From there you will see the two periodic orbit to period doubling, and you will hit the chaos. So here also I am saying that the same thing will happen, same thing actually happens from this single point to 2 point to 4 point to 6 point. So if it is the case, then the near about this and this, so near about very point should look like this whole picture. So let's see. Okay, let's go here, check the bifurcation. So we have to take these points. So from r minimum will be 3.847 to 3.847. 857. So I am taking only nearer region 3.47 to here. Let's see how it is, means how it look like. So okay, let me renormalize this thing. So I have done normalization. Oh, okay. You see that from 3.87, 847 to 3.857, you can see that the diagram is actually looking exactly similar. Only thing is it's become little bit tense because the number of points is lesser. If I increase the number of points more, then it will look exactly same. And you see here also, you see this at some point this period orbit become a larger window of 3 period orbit appears. So it hinted toward one thing, that this is quite self similar. If I zoom out any region of this all the orbit diagram, they all look like same. So this is called the self similarity or the universality of this chaos. So why, although it is quite chaotic, quite disorder in motion, that you cannot find any order in motion in there, but you see this chaotic thing also be self similar in nature, so that in between the chaos there is an intricate play, there is a intricate role of order is there. So we will see that this order is this mathematical term for describing this is called the fractal. So that we will see later, but for now we are let us convince ourselves that every point of the 3 point orbits actually if I increase r from little bit from 3 periodic orbit to little bit, it will go towards period doubling bifurcation, and by period doubling bifurcation you will find that the chaos will again appear, and the root of the appearing the chaos is quite similar to that was previous what we have seen for the single period orbit. So that's all. Is it clear, Subhusaji? Okay, if you have any question, I know that this becomes quite for the reference what I am saying, that since this is quite heavy to grasp, so reference is for this material you will I am following. So the Stephen Strogatz nonlinear dynamics and chaos by Strogatz, and it is the chapter 10. Okay, you can, for the reference you can follow that thing, the chapter 10 from this Strogatz. So you similar. Okay. Okay. Then next thing. No. After 2-3 class, because I want to. I planned that first of all I will. I love to mathematize that whatever I am saying, that the chaos means random, chaos means disorder, but it is only semantic, it is only language. what does mathematically mean the disorder, that I want to show. The first, so I need the 2-3 lecture for that, and 1 lecture for that thing, that universality, that some universality universal thing is there in self is a chaos. Then I will teach in this class I will discuss about the fractal. So maybe after 2-3 class I will start fractal. So that's one. So let's see another thing. So this is called the Lyapunov exponent. So we are saying that for sure actually, that we are saying that the chaos is there, but only what we have seen, that only aperiodic orbit is appearing in the orbit diagram, only aperiodic orbit. But for the chaos, another thing is needed, which is called the sensitive dependence of the initial condition. We haven't proved that in that region of the R, values of R, there is a sensitive dependence of the initial condition. So what does the sensitive dependence of initial condition means? So that means, suppose there are 2 initial condition, x0 and x0 plus delta. Suppose this delta or delta 0, this delta 0 is very close to 0, that means this and this initial condition are very close to each other. Now it says the initial dependence of the, so if means where, suppose after nth iteration, where this x0 will reach to suppose xn, and where this xn plus delta, which is near which was that initial condition which is nearly close to this x0, suppose it reaches to xn prime, x0 plus delta 0. Now we are asking, what is the difference between these two, xn minus xn prime? So previously what was x0 plus delta 0 minus x0, what was that? That is nothing but delta 0. So now what is this difference, delta n? So that difference is fn x0 plus delta 0 minus fn x0. So this is that. So now what is called that this what is the property of this delta n, from where we can say something about that there is a sensitive dependence of the initial condition or not. So if the system has sensitive dependence of the initial condition, then what will happen? Then you will see that this delta n, that after nth iteration, how this delta 0 means that how these two initial condition upon iteration become far away from each other. So you will see that delta n, the modulus of delta n is actually closely delta 0 exponentially. So you will see that if you observe that they are exponentially going further from each other. So exponentially means whenever in the first iteration delta 1 will be the first iteration, what will be the distance between them? That will be delta 0 into e to the power lambda. In the second iteration you will find that e to the power 2 lambda, and the third iteration e to the power 3 lambda. If it exponentially going further away on average, so if it exponentially going further away from one another on average, we say that there is a sensitive dependence of the initial condition. That means if this lambda is less than 0, then what we will say? That if lambda is less than 0, that means it is not going apart from each other. When we iterate these two initial condition, actually the x if this lambda is negative, then we can say that this delta n is not increasing, suppose 0.5 into n. So this delta 0, that the initial distance between the two initial conditions does not increases but it decreases with time. But if this lambda become greater than 0, then we can say that these initial the difference between the initial condition actually increases as we increase the time or increase the iteration. So this is the actually numerical way to calculate whether the system has a sensitive dependence on the initial condition or not. On average, they are going further apart or not. So how we can calculate? So the lambda means from here you can see. So lambda means delta n, lambda closely, lambda 0 into ln by 1 by n. So this is the from here one can easily calculate this, the lambda equal to 1 by n ln delta n by delta 0. So let it further simplify, lambda equal to 1 by n ln what does this delta n means? Delta n by delta n means this fn x0 plus delta 0 minus fn x0 by delta 0. Now we know that this delta 0 is very close to 0, so that means 1 by n ln limit delta 0 tends to 0, delta 0 is tends to 0, fn x0 plus delta 0 minus fn x0 by delta 0. So what does this mean? This actually means only differentiation. So this means 1 by n ln, this is nothing but the differentiation. If I iterate n times on x, that's differentiation at the point of x0. Now that's it. Now what we know that, so this is that things. So if so lambda exactly means if we take limit n tends to infinity, if we iterate it infinite time or large time, in computer this means large time, 1 by n ln, that will become fn prime x0. Now what we have seen that we know that f square x0, its differentiation means f of x0 and f of x1. And if I go similar way, you will find that differentiation of this fn x at x equal to x0, you will find that it is actually the multiplication of I equal to 0 to n minus 1. Here 2 means 0 and 1, so f of xi. So if you multiply n minus 1 and every time it's okay, this is the differentiation. So this is it, and here xi means that f of xi minus 1. So that means how you get x1 from x0? x1 you will get if you x0, and how x2 means f of x1. That's why you will get this x1 x2, and every time this prime and this prime, we know that for the logistic equation, the differentiation equation, so fx nothing but r into x into 1 minus x. So the differentiation of this at that point xi. Now if I put it here, so that will become summation by n limit n tends to infinity, summation of n equal to, so I equal to 0 to n minus 1 ln a prime xi. This is the lambda. So this is lambda. If this lambda is negative, then so obviously this lambda will depend on x0, but if you take on average, this dependence will be gone. Now depending on the values of lambda, will say whether or the not this system has a sensitive dependence on the initial condition or not. So that's it for the this class. Now we will see that some example where that lambda negative means the periodic orbit and lambda greater than 0 means the chaotic orbit. So that we will see in the next class, next Monday. So that's it. If you have any question, you can ask me, or else I will end this class here. And I will again repeat this Lyapunov experiment. If you have any question, then it will be much more clear there. Okay, then Sobhusaji, I am leaving this meeting, right? Thank you for joining.